Welcome back to Chemistry Fundamentals course. Imagine losing a 125 million spacecraft because someone confused meters with feet. That's exactly what happened to NASA Mars Climate Orbiter in 1999. Today we are going to explore why units and significant figures are absolutely critical in chemistry, not just for passing tests, but for preventing real-world disasters and ensuring scientific accuracy. Let's dive into the language of measurement that connects scientists worldwide. Units aren't just arbitrary labels. They are the foundation of scientific communication. The NASA Mars Orbiter disaster I mentioned, that happened because one team used metric units while another used imperial units. The result? A $250 million mistake. But it's not just space missions. In 1983, an Air Canada flight, now called the Gimli glider, ran out of fuel mid-flight because ground crew confused pounds with kilograms when calculating fuel needs. In medicine, unit confusion can be literally life-threatening when calculating drug dosage. This is why chemistry relies heavily on the International System of Units, or SI units. These 7 base units give us a universal language: the meter for length, kilogram for mass, second for time, and mole for amount of substance. While we will explore deeply later in the course, from these base units we derive everything else we need: volume, density, pressure, and energy. The beauty of the metric system lies in its simplicity. Everything is based on powers of 10. Think of prefixes as scientific shorthand that tells you exactly how to move the decimal point. For larger quantities, we have kilo, meaning 1,000, mega, meaning 1 million, and giga, meaning 1 billion. Your computer gigabyte of storage, that's literally 1 billion bytes. For smaller quantities, we go the opposite direction. Milli is 1,000th, micro is 1 millionth, and nano is 1 billionth. To put this in perspective, a nanometer is so small that if you enlarged a marble to the size of Earth, a nanometer would be about the size of that original marble. Chemistry deals with incredibly large and incredibly small numbers. Avogadro's number, the number of atoms in a mole, is 602,000 billion. And also we have the mass of a single electron is 0. You need here to add 30 zeros, and after that 911 kilograms. Writing these out every time would be impossible. Enter scientific notation, a way to express any number as a value between 1 and 10, multiplied by 10 raised to some power. The format is m times 10 to the power n, where m is called the mantissa and n is the exponent. Let's convert the number 1,500,000 to scientific notation. First, find the first non-zero digit, that's the 1. Place your decimal point after it, 1.5. Now count how many places you moved the decimal point to the left. That's 6 places. So 1,500,000 become 1.5 times 10 to the power 6. For small numbers like 1 point, let's add 3025, move the decimal point to the right until you get 2.5. You moved 4 places right, so it becomes 2.5 times 10 to the power negative 4. The negative exponent tells you it's a small number. Every measurement has uncertainty, and significant figures tells us exactly how precise our measurements are. They include all the digits we are certain about, plus one uncertain digit. Let's learn the rules. Rule number 1. All non-zero digits are significant. So 123.45 has 5 significant figures. Rule 2. Zeros between non-zero digits are significant. The number 1002 has 4 significant figures. Rule number 3. Leading zeros are not significant. They are just placeholders. So 0.00123 has only 3 significant figures, the 1, 2, and 3. Rule number 4. This is where it gets tricky. Trailing zeros are significant only if there is a decimal point present. The number 1200 has only 2 significant figures, but 1200 has 4 significant figures. And 1200.0 has 5 significant figures. Why does this matter? When you multiply or divide measurements, your answer can only be as precise as your least precise measurement. If you measure 2.34 grams and 0.892 milliliters, your calculated density can only have 3 significant figures, limited by the volume measurement. Dimensional analysis, also called the factor label method, is your most powerful problem-solving tool in chemistry. It uses the fact that multiplying by a conversion factor is the same as multiplying by 1. Here is the key insight. 1000 milliliter over 1 liter equal 1, because the 1000 milliliter and 1 liter are the same amount. You can flip this fraction to 1 liter over 1000 milliliter, which will equal 1 depending on what units you want to cancel. Let's solve a problem. Express 45,600,000 in scientific notation. Move the decimal 7 places left to get 4.56 times 10 to the power 7. How many significant figures in 0.0506? Remember, leading zeros don't count, so it's 3 significant figures, the 5, 0, and 6. Convert 3.5 hours to seconds using dimensional analysis. 3.5 hours times 60 minutes over 1 hour times 60 seconds over 1 minute. That will be the result, 12,600 seconds. The beauty of dimensional analysis is that it prevents unit errors. If your units don't cancel properly, you know you have made a mistake. These skills will be essential for every calculation we do in chemistry, from simple unit conversion to complex stoichiometry problems. Remember, precision in measurement and calculation isn't just academic. It's what separates professional science from guesswork. Master these fundamental skills now, and they will serve you throughout your scientific career. See you in the next lecture.